Right, so just to remind you of what we discussed yesterday, we discussed the simple worm-like chain model of a semi-flexible polymer and talked about how the ratio of the length to the persistence length was an important parameter in deciding whether we could think of this thing as a rigid object or not, as an individual entity. So what I gather what you've heard about this week is a lot of lectures about liquid crystals and probably a handful of lectures about polymers. Okay, so what today's lecture topic is going to be about is what are the properties of a liquid crystal in phase if it's made out of polymers. Okay, so it's exactly that question, and in particular we're going to be interested in questions of how these orientational degrees of freedom, which are essential for a liquid crystalline material, are coupled in a fundamental way to positional degrees of freedom. Okay, so how would I know what is the signature of being a polymer liquid crystal versus a regular liquid crystal? Okay, that's the simple question we're interested in. So before I get there, this is painful. Can you guys see anything there? Okay, so Jonathan Selinger, who has fled to some game preserve, promised me that he was going to discuss Onzaro Theory. So who here has heard of Onzaro Theory? Who here knows Onzaro Theory? I had a small handful. Thank you, Christina. Thank you. Okay, so this is a very simple model for how to understand how a system of rod-like hard particles undergoes a transition from an isotropic phase to an oriented pneumatic liquid crystalline phase with increasing density. Okay, and the question we're going to be talking about today is what happens to a system of polymers as it becomes more dense, as it enters what I'll call a condensed phase, either a polymer pneumatic phase or a columnar phase. So first we're going to start with this sort of reference theory of Onzaro Theory. So this is going to be a sort of a 1-minute overview of Onzaro Theory, and we're not going to do it in any detail, but I want to give you the essential idea. It's very simple in many ways. So the idea of Onzaro Theory is to balance the entropy loss associated with excluded volume interactions between two rods, right? So at low densities, the non-ideal gas of rods has some corrections due to the center of mass placement, say, of the second rod due to the exclusion of the hard core of this first rod. Okay? And the correction you would calculate from the Viral expansion in statistical mechanics. It goes as the concentration of rods, okay, times the excluded volume of the other rod. Okay, it's very simple. This is the reduction of the sort of phase space that's available to this rod due to the presence of this other rod. It's a simple calculation. And what Onzaro realized is very simple to calculate if you have a rod with a certain diameter d and length L. This excluded volume depends on the angle between the rods. Okay? So the excluded volume, it goes as sine theta times dl squared. So if they're perpendicular, they exclude the most volume. Okay, so that's the cost to be in an unaligned phase where sine theta is not 0. Okay, when sine theta is 0, there's a relatively low cost of excluded volume. And so you have to balance this, of course, with the entropy difference of being in an isotropic phase where every rod can enjoy pointing in every different direction. Okay, so there's more rotational entropy in an isotropic phase versus an aligned phase, which may have small wiggles around a preferred orientation, but a lower orientational entropy. Okay, so per rod, the entropy difference of being in the isotropic phase versus the pneumatic phase is of order 1, or the Boltzmann constant. Okay, it's not really that interesting to calculate what that number is. We could do it. But basically, the idea is that the rotational entropy difference is some number, whereas the center of mass entropy difference is linearly proportional to the concentration times the excluded volume per rod. Okay, so how do you estimate the transition from when it's preferable to be in this isotropic phase versus the ordered phase? Well, you basically set these two costs equal to one another and ask at what concentration that happens. We'll call that C star. And that's a estimate for when you would expect to go at low densities from the isotropic phase to the pneumatic phase with this hardcore model. And you can very easily take these two expressions, set them equal to one another, and you find there's a critical density that goes as 1 over dl squared. Okay? And if you multiply that critical number density, so the number density of rods, times the volume per rod, d squared times L, you get a critical volume fraction. So this is a critical fraction that is occupied by these hard cores, and this very famously goes as d over L. Okay? So this shows you that as you increase the aspect ratio, okay, L goes to infinity compared to D, the concentration at which you go from the isotropic phase to the nematic phase goes to 0. Okay? Very simple model. And it's a little bit more complicated than that because you really have coexistence as if you fix the density rather than fixing the pressure, but let's not dwell on that. So now let's go back to the case of worm-like polymers with the similar hardcore exclusion. Okay, how do we think about the Onzaro theory and the limit when L is very small compared to LP? This is the question I'm asking. What's different compared to the Onzaro theory, where L is small compared to LP?
We only have a flexible rod instead of a hard rod.
When L is small compared to LP, when L is small compared to LP, this is the limit where the rod remains rigid, right, over its length. Okay, so Onzaro theory should roughly still apply. Same prediction. Okay, so in the opposite limit, in L is large compared to LP, right, it extends beyond the persistence length. Globally, it looks like a coiled filament. And again, we have this kind of continuous filament picture. So what do we do here? How can we connect back to the Onzaro picture?
Instead of the length, we use the persistence.
Can you say that louder?
Instead of the length, we use the persistence.
The persistence length. So here's the idea. We take this continuous filament and we cut it up into a sausage lick, okay, of little Onzaro rods of length LP, okay? And so, in fact, now it doesn't even matter that these things are connected, right? Because the whole idea of the persistence length is that beyond this persistence length, the orientations of those two segments are not really correlated, okay? So they're relatively, at least fairly crudely, we can think of these as statistically orientationally independent entities. And now we simply chop the chain up into lengths LP, okay? So that basically tells you that the critical critical volume fraction should go as D over LP, okay, rather than D over L. So if you combine these two things together, you can see, in fact, that in the rigid limit, the critical concentration goes as 1 over L squared, whereas in the flexible limit, it just goes as 1 over L. And of course, people have tested this both experimentally and in simulations. This is a paper by Don Frankel and Miriam Dijkstra looking at the isotopic to pneumatic transition, and this is the scaled volume fraction versus the scaled length. And you see that for very short lengths, the critical volume fraction decreases as 1 over L until we reach roughly the persistence length. And so what I want you to take away from this, of course, is that as you sit at a fixed concentration, you decrease L, you increase L, you're going to increase the tendency to form a pneumatic phase. Okay, that's because the rods are longer, they're more likely to impinge upon one another. Okay, but at the same time, if you sit at fixed density, fixed total length, and you increase the persistence length, you also increase the tendency to form the pneumatic phase. Okay? So by increasing the intrinsic rigidity of the molecule, in some sense, you're sort of amplifying the interactions between them. Okay, so even though it's an intrinsic property of the molecule itself, it has an effect a very strong effect on the correlations and interactions and the collective behavior of the system. Okay, it's going to push you into the pneumatic phase at an earlier condition. So the intrinsic properties of the rod, the stiffness effect when this transition happens. This is again a very qualitative picture. So what we're going to talk about today now is sort of the inverse property. What happens now when we have a liquid crystalline phase, which is not composed of little small molecules, like sort of small molecule liquid crystals, but where the molecules themselves are long chains. Okay? And sort of the conceptual question, which will turn into a formal question in a few minutes, is really just kind of how do we take this equation, which is the Frank elastic free energy, okay, which has penalties for a splay deformations with some elastic constant K1, penalties for twist deformations, penalties for bending deformations. Okay, so these things are here because this is a material which has an orientational order parameter. It's really a tensorial order parameter if we're doing it carefully, but it's almost lunchtime. So we have this orientational order parameter, but at the same time, depending on sort of how dense the material is, there's also some type of elasticity, some response of the system to changes in either the density or the positional order. Okay? So at, say, low densities, we may have something that we'll call a polymer pneumatic or a line liquid, where transverse to the long axis of the molecules, you have some free fluid of the change positions, okay, but it still is an oriented material. Because it's a liquid, in a very sort of simple sense, we'll use a very, very simple phenomenological model, which says there's some preferred density, rho naught, okay, and there'll be some penalty for deviating away from rho naught at different points in space. Here's some modulus, we'll call it the bulk modulus B, and maybe there's some penalty for gradients. Okay, and probably higher order stuff that we're not going to really need to worry about. Okay, so if this is a fluid, we might expect some sort of density free energy expression. If we go to even higher densities, we can imagine the chain positions will freeze. Okay, and in cross-section, you could imagine some sort of two-dimensional lattice filament positions. This is what happens in these biological filament bundles when they're strongly interacting. And in that case, the form of the free energy that one described, we'll come back to this probably tomorrow. I don't think we're going to get here today. But the type of free energy that one needs to describe is a type of continuum elasticity, okay, where we have some reference state, some two-dimensional lattice, and we describe deformations of that lattice in terms of something that's called the elastic strain. Okay, how much have I locally stretched or sheared the 2D lattice packing filament positions, and that's described by some displacement vector. Again, we'll come back to this tomorrow and probably the last day. So for today, the basic question is how does this elasticity, the Frank elasticity that you've probably heard about 6, 7, 8 times already, how does this talk to the density elasticity? Okay, these are fundamentally and inextricably coupled in polymer pneumatic. Let us see. Great. Any questions before I try to address that? Okay. So in order to address that question, we need to define a little bit better kind of what is a reference state. So we want to understand what is the difference between a pneumatic by itself and a polymer pneumatic. Okay, so what we're going to do in the first few minutes is analyze the fluctuations of a pneumatic based on the Frank elastic energy. Okay, and then what we're going to do is add in the coupling between density and orientation and see how that coupling modifies the type of fluctuations you see, modifies the nature of the elasticity of the material. Okay, so you'll have to travel with me from real space to Fourier space. And so I'll need your help at times to tell me whether I'm on the right track. So, the first step is going to be to consider a pneumatic which is weakly deflected from, say, the z-axis. So imagine most of the molecules are pointing along Z, but occasionally at different points in space, we can have the pneumatic director wobble about, okay? And we'll do that by introducing, you saw something very similar in Christina's lecture this morning, tilts, delta n of x, okay? This is in the xy plane, okay? So the pneumatic is approximately equal to z plus delta n of x. This is the part that wiggles about in space. It's almost a unit vector, and we could fix it up if we really wanted to. So, okay. So in this case, when we go back to the Frank elasticity, which has these 3 types of coupling. Okay. So what is the coupling that corresponds to K1? see who's paying attention to the last lecture. Okay, one. This is the splay. So what is the splay operator? Splay is the divergence, okay? But in this case, we've assumed that all of the variation is in the x and y direction. Okay, so the only part of the divergence we're worried about is in the xy plane. So we can write this using some notation using the perpendicular gradient. Okay, so I'll define this to be the gradient only in the x and y plane. Okay? No big deal. Likewise, the twist, okay, the full twist operator is n dot curl of n. Okay, on average, most of n is in the z direction, so in fact, all we're interested in is the z component of the twist. Okay? Which I'll write as del perp cross delta n. Okay, this is nothing other than dx delta ny minus dy delta nx. Okay. I just want to make sure this notation is sort of trivially obvious to you. Okay, we're going to put this up and kind of leave it up there. And finally, the bend, which is n dot grad of n. So the bending operator, how does the pneumatic texture change when I move along the director? Okay, most of the time, again, it's the lowest order, n is pointing along z. Okay, so this is going to be the z gradient of n. And the only part that has the gradients are the tilts. Okay. So this bending is dz of delta n. Great, so now we have a nice Gaussian expression to second order in this tilt deformation. And now we want to ask the question, given this elastic energy, what types of fluctuations would I expect to see? Okay, so imagine I was doing some sort of polarized scattering experiment where I could measure variations and correlations in the orientation of the pneumatic at different points in space. Okay, and in principle, I should be able to detect the fluctuation spectrum of this pneumatic. So how do we do that? Well, the way this is easily done, or most conveniently done, is to convert our point of view to Fourier space. Okay? So here, what I'm going to do, is introduce the inverse Fourier transform. Okay, so this, of course, is some real space configuration of my pneumatic. This vector k, of course, is the wave vector. Okay, and delta n of k is just the Fourier transform of delta n of x. Okay, so this is the inverse Fourier transfer summing over all, if you like, plane waves of these of the pneumatic fluctuations. So why do we do this? Well, really the reason why we're doing this is that it's very easy to convert derivatives of this type to the Fourier space representation. Okay, so I'm going to introduce some notation that's going to allow us to kind of very easily translate this into Fourier space without going through the details. So the idea is, if I take the partial derivative with respect to the ith component of the spatial direction, okay, in Fourier space, that's what this notation means. Fourier space, this is equivalent to pulling down the ith component of the k vector. Okay, so why is that? Let me write it down and I'll discuss what I mean. Okay. So you can imagine this operation in the following. partial derivative, spatial derivative with respect to the ith component of the x direction. Okay, using this inverse Fourier transform, the derivative, of course, is just going to act on the ith component of the x direction here. It's going to pull down a factor I times ki. Okay, and so this is what I mean by this correspondence. Okay, so this is going to, as I said, this is going to very easily allow us to deal with these funny funny gradients, right? The divergence gradient and the twist gradient and the z gradient. Okay, so we need a little bit of technology to sort of enable us to look at this in the right way. So, any questions about this before I go on? I want to make sure this is thoroughly clear. Okay. So, what do we do? Well, so the sort of reason why we're doing this, again, is that, in fact, this is a two-component vector. It has components in the x and y direction, but that's not a particularly convenient basis for studying the fluctuations. Okay? So, in fact, we're going to use a way of analyzing the polarizations of these fluctuations in Fourier space, which is very convenient, right? It allows us to split this energy right up and just kind of stare at it and understand immediately kind of what parts of the free energy couple to splay, what parts couple to twist, and what parts couple to bend, right? These separate in a very nice way. Okay, so the polarizations that we'll use in Fourier space are the following. So we'll consider some Fourier mode delta n of k, and we'll split it into components that I'll call longitudinal. Okay, these are parallel to the in-plane components of k. Okay, so remember, this is only components in the x and y direction. This is in the direction of the wave vector in the x and y plane. That's what this notation means. And this is called the longitudinal mode. You may have seen this, for example, when studying phonons or excitations of some sort of elastic medium. Okay, and you can do you can look at the other polarization. Okay, which is called the transverse mode. In this case, it's very simple to write it. It's basically 90 degrees rotated with respect to the longitudinal direction, which is along k, which is perpendicular to k. So I just take z cross k per. Okay, and that gives me the other polarization. Simple. Okay, you'll see that this is going to make this expression very simple in Fourier space when we express it in terms of the longitudinal and transverse components. Again, a little technology will help us out. So first, let's look at the splay operator acting on this representation. So splay so in Fourier space, okay, again, this is going to be I, k, per dotted into the Fourier transform of delta n of k, right? Because the derivative operator just pulls down the appropriate components, in this case the x component times the x component of the nematic fluctuation, the y component of the wave vector times the y component of the nematic fluctuation. Okay, so I take the dot product of k per times delta n. What do I get? Or let me put it this way, what don't I get? So I take k per and I multiply it times the longitudinal component. What comes out? So the longitudinal component is parallel to k per. Okay? So this is just going to give me the magnitude of k per times the longitudinal component. What about the transverse component? 0. Right? By definition, the wave vectors is perpendicular to the transverse component. So this picks out only the longitudinal mode. Okay, so splay only couples to the longitudinal mode. That allows us to separate those two modes. Okay. Very nice. Tudinal. How about twist? Again, this is going to be IK cross dn of k. So if I take k cross the longitudinal mode, what comes out of that? 0, right? Because this is k cross itself. Okay, the cross product between k and itself is 0. The only thing that's going to be left is from this this last term. Okay, we're going to have to use one of those cross product identities here, and I'll just tell you the answer, which I worked out on the airplane. Okay, what comes out of this? Essentially, what comes out of this is just the magnitude of k. Okay, you can check. You check and tell me if I did it wrong. It's actually the magnitude of k times z hat. Magnitude of k times the transverse component times z hat. So I only have the transverse component here. Okay, so twist only couples to the transverse mode. Splay only couples to the longitudinal mode. And what about bending? Well, so bending now is the z derivative of the pneumatic fluctuation. Okay, so this pulls down not kx or ky, which are in the components of k perp, it pulls down kz. Okay, so with respect to k perp, there's no particular different orientation here, right? So in fact, we have ikz times both modes. Okay, so both modes generate bending, although in perpendicular directions. Okay, so there's both transverse fluctuations, longitudinal fluctuations and transverse fluctuations give you bending. So that means that the energy cost for both polarizations should have K3 in it, while only the longitudinal mode will have K1 in its cost, and only the transverse mode will only have K2. Okay?
Bending in the plane is higher order here.
Bending in the plane.
Yeah.
Bending in the plane must be higher order at delta n.
Because you have to project onto the delta.
You have to project, right? So there's the lowest order, the first order, in the Gaussian. Okay, so all I'm going to do is take these expressions, plug them back in here, and Fourier transform this integral over all real space to an integral over all Fourier space. Okay? So I'm going to rewrite this in its Fourier representation, and I'm happy to discuss all intervening steps, but what I really want to emphasize is the results, and which we're going to use. I sacrificed my childhood. Very good. Okay, so in Fourier space, I have a sum over all polarizations, all wave vectors k, rather than over all positions. Okay, and I don't want to dwell on the steps. Okay, but first I'm going to talk about the modes that couple to the longitudinal fluctuations. Okay, so from this operator I get k perp squared times k1 plus kz squared, plus k3 times kz squared times the amplitude of the longitudinal fluctuation squared. Okay, there's no k2 here because there's no k2 cost for twist, right? Twist is perpendicular to the longitudinal mode, and likewise down here, there's no splay cost for the transverse mode. Okay, but the twist of the transverse mode goes as K2 times K perp squared. K perp coming from the curl of delta n. Okay, times the transverse mode, and there's still a K3 component. K3 times Kz squared, delta n transverse squared. Okay. So now we get sort of we've made some progress. I guarantee you. Okay. What we've done is we've grouped these two polarizations into two independent modes in Fourier space. Okay. The cost for amplitude fluctuations in either the longitudinal direction or the transverse direction is simply depending on the magnitude of the wave vector in the plane that's perpendicular to the nematic orientation or along the direction of the nematic orientation. Okay? And we see now that these costs for longitudinal fluctuations depend on splay, but not twist, and the costs of the transverse fluctuations depend on twist, but not splay. Okay? So if I was to independently analyze the in-plane fluctuations scattering in the plane of these two different modes, I could in principle have a way of piecing out how big is K2, how big is K1. So, what we in principle could do is do some experiment where we observe the equilibrium fluctuations of the longitudinal components, okay, at finite temperature. So given this form of the energy, what would you expect for the mean square fluctuations of the longitudinal component at finite temperature? I have some energy that goes as the amplitude of that mode squared times some constant. Let me ask a different question. Let's say you had a very simple model where your energy is equal to 1/2 k x squared. And you ask yourself the question, what is the equilibrium expectation value of x squared? Say a letter.
2 inver k.
There's a theorem, I think, I can't remember.
Yes.
Equipartition, I think that's what it's called, right? Somebody else say something, say it louder.
I think it's a fluctuation dissipation theorem.
Yeah, it's related to fluctuation dissipation theorem. Okay, so this is the equipartition theorem, which I know you know somewhere in your catalog. Okay. If I have a harmonic mode, an independent harmonic mode with some spring constant k at finite temperature T, the equilibrium expectation value of that mode squared is the temperature divided by the spring constant k. So this is obviously more complicated, right? These spring constants, and I apologize, I've been told that I use the letter k, right? So k appears in sort of every formula in a different variation. But you don't want to see what it looks like when I draw a cube. Okay, so in any case, this spring constant, which would go in the form of the effective k for this longitudinal mode, is this combination of variables here. Okay, so every Fourier mode has a spring constant. In this case, k1 times k perp squared plus k3 times kz squared. Okay. So this is really nothing other than kt divided by k1 k perp squared plus k3 times kz squared. Okay? So again, if I had a way of observing the fluctuations at different wave vectors in the plane and out of the plane in principle, I could try to match what these coefficients are. That would be useful. Okay, so likewise, the transverse component, which doesn't depend on splay, but only on twist and bend, is K2 over K perp squared plus K3 over Kz. all the technology we need. Now we need to sort of step back and think about how this is going to work for polymer pneumatics. So this is the reference state. This is what boring pneumatics would do. You just watch them at finite temperature, non-active. You know, these are lazy pneumatics, right? They're passive. So they will fluctuate in some wave vector dependent way. The different polarizations will depend on the different elastic constants. So now we have to ask ourselves the question, given this sort of spectrum of orientational fluctuations, what is the essential ingredient we need to add for the case of polymer pneumatics that's going to relate the density fluctuations to the orientational fluctuations. And so here we'll draw some pictures to illustrate. And it's a very beautiful idea, right? And so I certainly hope you find it out. So this is for the case of a polymer pneumatic. And what I'll call this is conservation law, for reasons that will be very obvious. And probably the original citation is Dijon, or at least it's the one that everyone says is the original citation. And that's probably 1977-ish, right? So we like to bring up things that happened in the 70s. I think Bob Meyer, probably 1982, you'll find as two main references for this picture that I'm about to show. Okay, very simple idea. Okay. So in a polymer pneumatic, the only difference, of course, is we have this microstructure of these long chains. Okay, so I don't have little short chains, these chains are extended. So microscopically, I have something that looks like this. Okay, where my pneumatic director, of course, is oriented along the backbone, say along the local tangent of this curve, or the coarse grained average of the neighborhood of tangents. Okay? So I, of course, have an orientational degree of freedom for a polymer pneumatic. I can tell you on average, all of the polymers at this point X, or within some neighborhood of X, they are pointing along the pneumatic director. But that's not the only way I can describe this system. Okay? In fact, I can think about, in addition, let's see if I can try to draw the picture a little better. I can think about the density of chains at some given point. Okay, so let me introduce another operator. Okay, I'll call that rho of x. Okay, rho of x is the areal density of chains transverse to n. Okay, just the number density of chains. Okay, so I have these two order parameters. I have n and I have density. And again, this is at some finite temperature pressure, so there's some preferred value of this density. The pneumatic director, at least in an achiral system or simple boundary conditions, always wants to point in the same direction. So here's what we can do. Let's take these two things and multiply them together. Okay? And what we'll call that operator, we'll call that J. So that is going to be the areal density of chains times their direction. Okay? I'm going to make our lives simple for today. We could do things more complicated. I'm going to put little arrows on these chains and pretend they're polar, even if they're not. Okay? We don't have to, but let's, again, let's cut to the chase. So J, what might you call this thing? Right? So imagine these are little arrows. Imagine I put say some flow of something through them. What would you call J? The flux. Okay? So this is the flux. The number density, or the areal density of chains passing through some area element, I'll just call it passing parallel to n. Okay, so I put some area element in my material. Okay, and I just count the number of chains that go from the bottom to the top. Okay, and I can change the orientation of that area element and calculate the flux accordingly. Very simple idea. So what do you think we should do with this flux? What do we do with the flux? We talked about the flux of, not momentum, I guess the flux of particle number earlier, I think. Right?
We wrote a conservation of number density, like based on the flux.
So that's what we would want to do if this was a dynamical flux. So let's see if that makes sense for a polymer pneumatic. Okay. So how do we do that? Well, usually when we want to derive a conservation law, we take our flux and we consider a little element of volume. Right? So this is some box somewhere in my sample. Okay, and let's see, for this box, let's imagine that there are some number of chains coming in from the bottom. They could be coming in from the sides, doesn't really matter. Okay, and some number of chains coming out. Okay, so what do we do with the flux? We're going to take the flux, integrate over the surface area that surrounds this box times this flux. Okay, so what does this give us? So you can imagine in this picture, so if the normal area elements are pointing outward, what's the sign of the flux here? Doesn't really quite matter how I do it. If you want me to point the area elements in, I will. Okay. But so here the flux is inward, right? So I'm going to get, let's say, a minus sign. Okay, here, when the chains are going out, I'll get a plus sign. Right? Okay. So what is this going to tell me? This is going to tell me the difference of the number of chains that leave minus the number of chains that enter. Number of chains, leaving minus the number entered. How many chains leaving and entering should I have? Am I allowed to have any arbitrary number of chains leaving and entering? Are these allowed to be independent?
That depends on the accumulation or
What?
of the chain, of the number of chains, or like accumulation or product generation. And it could be a source or
Well, a source. Yes.
So if the box is small compared to the length, then this should be 0.
Well, maybe. It depends on what's inside. Okay? So let's try to draw a picture. Okay? Let's imagine, of course, this chain, it goes in and it comes out. So one end coming in, one end going out. That's going to give no net difference to the flux. This one goes in and goes out. But let's imagine here, these guys, they end, and this guy ends. So I have a different number of the population that goes in versus goes out. And that's telling me something about the net number of ends in the box. So if this is non-zero, if the number, and this you can do, this is an experiment you can do, right? Over the course of a day, if the number of people that enter the room is not the same as the number of people that leave, there must be people still in the room, right? This is true. Okay, so this is different. This is what we'll call the difference in the number of plus ends minus the number in minus ends. Okay, I'll call a plus end where a chain starts. Okay, and a minus end where a chain ends. Okay, and I can do that because I put little arrows on these chains. Right? So it's identical, fundamentally identical to what you learned in electrostatics. If I have flux of an electric field leaving a box, there has to be a monopole in there. Okay? So if I have flux of chains leaving this box, there has to be a non-zero density of ends. And so now, if I use Gauss's law, okay, where I convert this integral over the surface area to a volume integral of the divergence of curl, what I get in the continuum limit for Gauss's law is the divergence of this flux is equal to the density difference between the number of plus n's and minus n's. Okay? Density of plus and minus n's. Okay? Make sense? Now, what do we expect this density of number of chain ends to be in the limit that L, the length of the chain, goes to infinity? I said fixed density. Somebody said 0. Why 0?
Like I said, the most of,
So the concentration of n's at fixed volume fraction depends inversely on the length. So as I imagine taking the length of this chain to infinity, the number density of n's is going to be 0. There are questions? Some questions or a comment? Yes?
within the, I mean, if your box is also infinitely large, then
So certainly in my system there have to be some globally some number of n's, but now in Gauss's law, of course, we shrink the box down infinitesimally small. Okay. And so this number becomes a number density, and if on average the concentration of n's is small, which is somehow related to the length of the chains, I would expect therefore that whatever this funny flux operator is, the divergence of this flux is 0, okay, for very long polymers, okay? So again, this is nothing other than sort of our usual electrostatics. Now, how do we apply this to the case of polymer pneumatics? Okay, so in polymer pneumatics, the flux is the product of the density times the direction. Okay, so the derivative in the gradient and the divergence acts on both parts. Okay? So if I take the flux, the divergence of this flux, there's two parts. There is n dot grad of rho. Okay? This is, I'm just applying the chain rule here. Plus rho times divergence of n. Okay? And this has to be 0. Yes, sir?
I understand when you see the divergence of the flux goes to 0. I don't understand why the number density for the plus and minus goes to 0. Like the statement you were saying.
So essentially the idea, and I don't want to go through too many details here, but okay, so the density of plus and minus n's, okay, somehow related, and now I'm going to put some squiggly lines here before I make a horrible mistake, okay? It's somehow related to the number density of chains times the probability that a given point on the chain is its end. Okay? And so that's going to be something like C over L. Maybe there's a factor of D there or something to make it appropriate dimensions. Okay. And so my system has a certain concentration based on sort of how much space is filled with polymers and the number density. But as the length goes to 0, the probability that any given point, which is occupied by a polymer, is an end, is going to go to 0. So this is not strictly obeyed, okay? And corrections to what I'm going to tell you appear, and you should ask me if you want how we would do that. But let's just follow this line of reasoning and see where it goes. Okay, so this says if the divergence is 0, it says that this n dot grad of P has to be equal and opposite to rho times the divergence of n. Okay? Or in other words, okay? So we find now fundamentally these two types of modes, the density mode and the orientation mode, are inextricably linked. Okay? They're slaves together. Okay, so what is this? What is this thing here? Divergence of n. Divergence of n. So somewhere up there, right? It's the split. Okay, so this is one of these modes for an elastic deformation of orientation. This is the gradient of rho, the gradient of the density along the pneumatic direction. So this is just a derivative of the density. It says the derivative of the density is related to the split. Okay? Density gradient. So what? Okay, so that's the law, the conservation law for polymer pneumatics, and now let's see what that does. So we're going to again use the idea of taking a system which is almost homogeneous and consider weak fluctuations of that system. So, for example, we'll consider rho of x to be equal, almost equal to the preferred density plus some perturbation of the density. This is exactly the same form that we saw in Christina's lecture this morning, delta rho, which is some function of x. Okay? And so the gradients, of course, are only going to act on delta rho. So this transforms in this limit where we have a weakly deflected pneumatic almost always pointing along z. This says the z derivative, which is the derivative along n of delta rho of x, is equal to minus rho 0 of grad perf of delta n. Okay, this is just translating this to the sort of small Gaussian fluctuation limit. Okay. Great. So now we'll go to Fourier space. Okay, so in Fourier space, this z derivative just becomes kz. And in Fourier space, the del perp of delta n becomes what? Times dn, but only the longitudinal component, right? So the divergence picks out the longitudinal component. This doesn't couple to the transverse component, right? Remember how there are these two polarizations, the longitudinal component, which is along K perp, and the transverse component, which is perpendicular to K perp. This only couples to that longitudinal mode. Okay? So in Fourier space, what we find is one of these two polarizations is locked to the density. The other one isn't. Okay? So now we're going to see what happens because of that. Good. So we're going to do two things. This gives us a relationship that if I tell you what the density fluctuation is, I can tell you what the longitudinal fluctuation is at a given wave vector, or I could do the opposite. If I tell you what the longitudinal fluctuation of the pneumatic is, I can tell you what the density fluctuation has to be that's conserved. Okay, we'll do both and try to analyze what that tells us about the effective elasticity of the system. But in order to do that, we have to introduce a model for the free energy of the liquid. And we're going to use this very simple model, again, where the density has some preferred value every point in space, and just to be on the safe side, we'll add a square gradient term that says that the density wants to be homogeneous. You can imagine much more complicated interactions and gradients than this, but this is the simplest theory you can write down to refer things next to. Okay, so what we're going to do is we're going to take this relationship here, and we're going to use it to solve for delta rho of k as a function of a given longitudinal fluctuation. Okay, so all I've done is flip kz to the other side, and all I'm going to do is plug it back in here. Okay. And you're going to notice something funny, that for K perp constant, but Kz goes to 0, what happens to the density fluctuation? So K perp is some finite number, Kz is 0. It diverges. Okay. So this is going to give us some funny signature in the free energy. And I'm really, for this part of the story, I'm just going to deal with this first term. I'm going to forget about the gradient. We'll put it back in later, but it's not so interesting. Okay, so if I convert this to Fourier space, and again, we can worry about the details at a more civilized hour. What do I get when I plug in? This is, of course, delta t of x. I plug in this Fourier amplitude. Okay, I'm going to get some factor of rho squared, k perp squared, delta n squared over kz squared. Okay? So I get an extra term that couples to the longitudinal fluctuation. It also appears with a k perp in front of it, k perp squared, but it has this funny 1 over kz squared. Okay. So now in this last step, all I'm going to do is take this and group it with that. Okay, put it all together and see what it looks like, trying to interpret the form of the energy as if it was a simple nematic. How would I think about this if I were thinking of it as a simple nematic? If I had that expectation. So let me just tell you the answer, and let's see if it looks like it makes sense. And I want to get very quickly to one last point and give you a puzzle to digest over lunch. Good. Okay, so all I'm going to do is take the Frank energy plus the liquid energy with this bulk compressibility term. I'm going to shove them together, squish them together. Okay, so F effective is now 1/2 times the sum over all these Fourier modes. Okay, first off, you'll notice that the transverse mode, the response in the transverse direction is the same, right? Again, the density doesn't affect the transverse fluctuations and orientation, so we'll just write that first. K2 times K perp squared plus K3 times Kz squared times dmt, the transverse mode. But K1, the longitudinal component has both the original response of the nematic, okay, which has some K1 some cost per splay for the perpendicular derivative, but it also picks up this extra piece that depends on the compressibility. Okay, so this is from the coupling density. Sorry, I'm missing something over here. This is all multiplied times the amplitude of the longitudinal expression, of the longitudinal fluctuation. So the very last step is going to notice that both of these terms are perpendicular to K perp. Okay, and so what I'm going to do something clever. Okay, I'm going to define some new K1. I'll call it K1 prime, which is now a function of my wave vector K. Okay, so I'm going to redefine some other variable K1 prime that's going to allow me to group these two things together and make it look as if it's the regular free energy expression for a simple nematic. Okay, so now what I get, right, you can see what I did here, I'm going to combine these two things, and what I get is going to be a renormalized splay constant. Well, sorry, splay cost. Now it's no longer constant. So K1 prime as a function of K is equal to the original splay constant plus, all of this stuff, except for the K per squared, okay, plus B rho squared, the compressibility times the mean density squared over Kz. Okay, so this is now a very funny nematic where the response of the material, what you would call its elastic properties, are now wavelength dependent. Okay, now wavelength dependent has to do with this inextricable coupling between orientation and density. Okay? And in particular, there's something quite remarkable that happens here. If I take the limit of taking a system, imagine I just put a homogeneous splay. Okay? I take K goes to 0, Kz goes to 0, this splay constant goes to infinity. Okay? So, as K goes to 0, K1 prime diverges, that means that splay is infinitely expensive. No way you can have splay. So what's going on there? Why is somehow something that was some finite cost somehow become infinite energy? We'll have to stop now.
Because the chains are very long.
Yes.
It is easy to twist them. I mean, they can twist with respect to each other.
Yes.
But if they want to splay, because of their long length, it is more expensive than.
So the picture you should have in your mind, and this is very intuitive, is the following. Imagine you have a splay for these very long chains, but you have no ends. Okay, a uniform splay necessarily requires a huge gradient between density at the bottom and the top. Okay, so the density is the, if you like, the areal spacing of the chains transverse to Z. This has to diverge if you have no ends. Once you have ends, right, eventually you can start filling things in at equal density and so on. Okay, so without ends, splay is infinitely expensive. So what I'm not going to do I'm not going to take a lot of time to do, but I want to get to the punchline in the puzzle. Okay, so we could do the opposite thing, where instead of solving for delta rho as a function of the orientational fluctuation, we can also solve for the orientational fluctuation as a function of the density fluctuation, which is going to be Kz times delta rho divided by K per times rho naught. Okay, there should be a minus sign somewhere in there. Okay, and substitute that back in to the Frank elastic energy on the top. Okay, and then ask the question, how does the energy depend on density fluctuations as delta rho squared? So if I were to look at the energy dependence of order delta rho squared and look at the fluctuations of density as delta rho squared, that would give me the structure factor. And this is what you would measure in a scattering experiment where you're measuring density-density correlations in the system. So let me just show you what those look like, and then I want you to explain it to me. Let's see if anybody can explain it to me. I think I understand it, but I've never seen it written down. Maybe Christina. Let's see. Okay, so you do that, and you get this answer. Okay, so first off, if I didn't have this nematic coupling here, okay, this is what I would get. I get 1 over the compressibility of this material. Okay, so this thing in the denominator is all the terms that multiply the density, cost for density fluctuation squared. Okay, these terms appear because of the coupling between density and orientation. Okay, so there's a K1 term that goes as Kz squared, and there's a K3 term that goes as Kz to the 4th over K per squared. And if you were to plot this in mathematics, which I did this, okay, you see this thing, and it's called a butterfly pattern. Okay, and this is the signature of fluctuations of a polymer in matter. Okay, purple, dark purple are where the density fluctuations are 0, bright colors in white are where density fluctuations are high. Right, so you get very large scattering transverse to the directions along which the molecules are oriented. And basically, density fluctuations are extinguished along this line. Right? Very peculiar. And where that comes from, it has to do with the divergence of this term. If I sit at a fixed kz, right, a fixed wavelength of density along kz, and I consider the case when k perp goes to 0, this term diverges. Okay? So I have 1 over infinity, which is 0 all along this line. So why does that happen? So you could say it happens because there's some term that's proportional to k3 in the denominator that goes to 0. But what that means is somehow the cost of creating these fluctuations along these lines are very expensive in terms of bending. So the previous picture we were talking about said that there's an important coupling between splay and density, okay, that made splay expensive, uniform splay deformations infinitely expensive in the long chain limit. All of a sudden now there's this penalty, apparent penalty that corresponds to the bending stiffness of your pneumatic that is prohibiting these fluctuations. So why does this cost so much bending? And I'm just going to leave that as a puzzle to you. So if anybody can explain it. Does anybody know? I asked Jonathan Selinger, who I thought should know. I mean, I know he knows, but you see lots of pictures for why splay is so expensive, but you see the spectrums quite often, but I hadn't quite had a simple explanation of why bending is infinitely expensive as k perp goes to 0 at finite kz. So, okay, so with that, I will conclude for today. Tomorrow, we're going to talk about columnar phases and twists. Okay, this is going to be very quick, but we saw that in a polymer pneumatic, of course, splay becomes infinitely expensive. In a columnar material, certain types of twist become infinitely expensive, right? It has more order and it starts to freeze out more of these fluctuations. But then we'll kind of revisit that in terms of certain special structures that form entire polymers. Okay. So, like I said, please, please bang your head on this for a bit and try to give me a simple explanation. Okay. Enjoy lunch.